Well, good afternoon. I'm going to have to be very quick today because we're going to cover the subject of quantum computing in 20 minutes. And we have with us today Richard Hopkins, the Senior Quantum Ambassador from IBM. I love that. It sounds like he's coming from outer space. But Richard is a fellow of the Royal Academy of Engineering and, as I said, the Senior Quantum Ambassador for IBM. He does a lot of exciting things, but you've read his CV twice, so I shan't repeat it because you want to get to the meat of the matter. We're going to be covering, as I say, quantum computing, and it's an area that we here at CN have been involved with really since we started, in fact, slightly before we started in 1994, having helped to establish the European Institute for Quantum Computation back in 1997 and running some trials on quantum encryption, which is a different subject, with the Bank of England in '99. So anyway, you know me, I'm Michael Mainelli, I'm one of the directors of XEN, and it really is a privilege to be able to introduce so many of these fantastic and interesting webinars, which we're only able to do thanks to the tolerance and generosity of our sponsors, who do allow us to range widely and freely across technology, economics, and finance. And you might say, well, what's quantum computing got to do with technology, economics, and finance? Well, in a sense, probably everything. Looking at the future, certainly technological. We're going to be talking about the economics, and as an economist and a statistician and in fact a computer scientist, I've always been interested in the application of this to optimization problems. In particular, for me, the traveling salesman problem, but there are a couple of other problems there that Richard will, I'm sure, touch on, and we can go on with the questions. So it's definitely in those areas. And in finance in particular, we've had a couple of webinars on people already using bits of quantum computation in portfolio and load balancing issues. So definitely a matter of interest to all of us. Meanwhile, the agenda today, as ever, is the same. I'm going to get out of the way as quickly as possible so we get as much time with our expert, Richard, and 3 points of housekeeping. Yes, this is being recorded. In this unusual circumstance, no, the slides will not be available. The recording will be in approximately 2 working days, so it should be up sometime Thursday afternoon. And the third bit is, how do you participate? What is this Q&A stuff? Please type your questions, comments, observations into the GoToWebinar chat room. Richard will get a copy of everything with your email attached, so he can get back to you. If you want to point something out to him, feel free to, whatever. I will weave those into a conversation with Richard, but please do use the GoToWebinar chat room. I'm not looking at my emails. I'm not watching Twitter. I'm not on Signal or WhatsApp or WeChat. I'm here with you. So please use the facility there to communicate to Richard what you'd like. Well, I think that's my 3 minutes, so hopefully we're going to get this thing done in 20. Richard, may I start with a really quick poll of everybody? Do you think you understand quantum computing? Yes, no, or somewhere in the middle? I have a basic understanding. Richard, we have a very opinionated audience, fingers on the buzzers, over 50% have voted, as I expected. Oh, we're going to get this thing done in 19 minutes. I can feel it. We'll just present those results, but most of the audience haven't voted. And the answer is, Richard, you're speaking to an audience who believe that they could really benefit from your guidance. So with no more ado, Richard, may I hand over to you? The floor is yours.
Thank you, Michael, much appreciated. So back to the beginning and 20 minutes. So we are a small planet. We have big problems. We all know that. And quantum computing is important because we think it could be the mechanism by which we start to approach problems that we find intractable today. For example, fixating nitrogen without using the Haber-Bosch process takes about 1.5% of the world's gas supply to create the fertilizer we use. Plants do it with an enzyme. Perhaps we could do the same. Catalysts to capture carbon dioxide. New ways of modeling financial futures so that we can increase the stability and the predictability of the health of banks and financial institutions, or possibly even, in the areas of molecular chemistry and looking at things like the nature of antibiotics and drug-resistant antibiotics. These are all terribly, terribly difficult problems. Quantum won't solve them directly, but it can or could provide, if we get the engineering right, the mechanisms to approach those problems in ways that we've been able to do before. So IBM's goal as a provider of quantum computing is quantum computing that is useful to the world. You know, we're not interested in computing the Gaussian distribution of bosons. We are interested in doing real world stuff, and also, whilst we're about it, making the world quantum safe by using quantum safe algorithms, which we've been working with NIST on a lot. The roots of quantum computing come from Richard Feynman of Manhattan Project fame and elsewhere, but of course also quantum mechanics. And his view was that if you wanted to understand nature in any level of detail, then you actually had to use a quantum computer. No one really knew what a quantum computer was at that point, but we've been struggling with that question for some time. You'd think with today's supercomputers that we'd be able to solve pretty much any kind of problem. When you look at the raw power and computational capabilities, we can simulate all kinds of things. We can actually compute incredibly complex reactions and capability. But the trouble is that a lot of the things we work with in the scientific field are exponential problems. They double every time you add a new factor into the equation in terms of the complexity. So there are a whole bunch of questions that, such as the traveling salesman thing we talked about earlier, that we simply can't adequately address today, even using the world's most powerful supercomputers. And of course, the other thing is that, you know, as we bring on board supercomputers and ever more powerful machine learning algorithms, you know, we are doubling the power that we use for these kind of things every 3.5 months at the moment. Okay, that's a hell of a curve, and we've got to get off that kind of route of burning more and more power to be able to make scientific progress. So we think quantum is at the heart of being able to do that. Why? Well, look at a relatively simple molecule like caffeine. Okay, just to model caffeine would actually require a classical computer with roughly the same number of bits as about 10% of the atoms in the Earth, 10 to the 48. Okay, that's not possible, and that's one of the reasons why we're still stuck with the Haber-Bosch process over 100 years since it was invented, with all its inefficiencies and everything else. We can't understand the process of that enzyme, nitrogenase, well enough to be able to model it, to be able to turn it into a catalyst. So quantum has that capability. Let me explain why in those 20 minutes. So this is what a quantum computer looks like today with its clothes off. Thankfully, I've got my clothes on. But this is a cryogenic chamber in which we actually cool the quantum computer down to about 13 millikelvin or so to ensure that the outside world is isolated away from what's going on inside the machine. Because what we're doing is kind of the reverse of CERN. CERN blows things up with using huge amounts of power. We are trying to manipulate the incredibly small and delicate using absolutely minuscule amounts of power. You may remember that back in the 90s, IBM spelt his name using xenon atoms by placing them on, you know. This is a direct result of all that technology coming through to enable us to get down to the ability to manipulate the very small. That allows us to create a quantum computer that uses the capabilities of the very small. So today we use bits. You're all familiar with bits, zeros and ones. And hopefully you're all familiar with how we use bits, which is in logical circuits. Quantum computers use something called qubits. Now, qubits are a little bit different. A qubit that's in a coherent state can occupy anywhere on the surface of that sphere, or on the block sphere. And the kind of program you can do on it looks remarkably like, for those of you who used to use machine code in the or assembler code in the 1980s or before, as I used to. We can act on quantum qubits using gates. So these are gates that are enabling us to manipulate one or more qubits to do certain things. So they kind of feel very similar to normal computers of today. You've got bits and qubits, and you've got gates versus instructions. What's the real difference? Well, the real difference is that the combination of any qubit can be in both the 0 and the 1 state simultaneously. When you measure it, Schrodinger's cat, you always end up with a 0 or 1, but fundamentally, as its computation goes through, you can get each qubit into a superposition state of 0s and 1s, which means that there's essentially a little bit more information in a qubit than there is in a normal bit in a computer. And you can do normal things. You can flip between a 0 state and a 1 state by using an X gate as shown here. Or you can do some things that are a bit more unusual, like the Hadamard gate, which allows you to actually rotate the state of the qubit from being the 0 state to sitting somewhere on the equator, okay, by rotating it through 90 degrees. Now it's got a 50% chance of being in the 0 state or 50% chance of the 1 state, 0 state when you measure it. But until you measure it, and the thing you've got to get into your head is, it's in both those states, equally likely. Well, that's not really where the power comes from in quantum computation. Where the computation power comes from is that when we write down the states of those qubits, here it is, we've got a qubit represented as those two different states, a mixture of 0 and 1. When you've got one qubit, that's fine. But when you entangle qubits together so that mathematically you can't separate out their states, you'll notice that 2 qubits can now only be written, because they're entangled, as 4 qubit state dimensions. So suddenly we've doubled the amount of information that's in there. But you say, well, we've doubled the number of qubits. Yes, but this is an exponential problem. So every time we add another qubit in, it adds another set of dimensions, which increases the number of state dimensions, as you can see on the picture there, by a factor of 2. So all those really hard exponential problems we were talking about, where you put another thing into the mix, it doubles the difficulty of solving the problem. And there's lots of those problems out there that we don't tackle in business today simply because it's too hard and it would be too expensive to tackle them. Well, a quantum machine can use this ability to double the number of states for every entangled qubit to enable you to get to some very large numbers of states with relatively small numbers of entangled qubits. And this is using that fundamental force of nature of superposition and entanglement to enable us to represent those states within a coherent quantum computation capability, i.e. within the quantum computer. So today we have, last year we announced the Eagle chip, which had 127 qubits. So the number of states that it can potentially represent is quite large. And recently, a few weeks ago, we announced the 433 qubit chip. So the number of states it can represent is somewhat larger than the number of number of atoms that are observable within the universe. Okay, so this is why quantum is different. It doesn't compute things in the same way. It doesn't parallelize things. It doesn't run algorithms in the same way. You create complex states essentially in the qubits that are entangled together, and then you use interference and various other techniques to ease the information out of the quantum machine, usually by running the program many thousands of times, so you can actually get out a probability distribution curve or an estimate of what the quantum computer has been asked to look at. Now, this all may sound like science fiction to you, but quantum computing is real. We've had over 50 quantum computers on the web since we put them there in 2016. A lot of them are free to use. You can go on there right now and play with them. We're running about 4 billion circuits a day at the moment, okay? Now, not one of those circuits we've run so far has managed to do something that a conventional supercomputer couldn't do, all right? So we haven't got to the point where we've declared victory with quantum computing, saying this is, a commercially viable proposition for everyday use, but that's what we're working on, okay? So it's an incredibly exciting field, and but by the way, that's what the quantum computer looks like with its clothes on, okay? And the key areas where we're going to see quantum computing being important, initially it's in the area where the metaphor distance, or the translatable distance, if you like, of what the quantum computer can do versus the actual real world metaphor analogy that we're trying to get to is relatively small. So if you want to model a quantum system, as Richard Feynman said, the best thing to do is use a quantum computer. So for quantum chemistry, for material science, high energy physics, CERN, for example, are using quantum computers to help develop the kind of computations to maybe understand dark matter and dark energy and this kind of thing. So initially, we're going to see those scientific applications coming through, but they're quite exciting. I've covered some of those at the beginning of the presentation. They are potentially world-changing things in their own right. Not far behind them, though, is artificial intelligence. Recently, we created a machine learning model based on the smarter payments software that IBM uses, which basically runs a lot of fraudulent, detects an awful lot of fraudulent transactions in the real world today. I think most of the transactions in financial transactions in France run through it, for example. We were actually able to stand up a quantum machine learning algorithm side by side with the best, XGBoost and random forest algorithms side by side, and got very similar results, even on today's noisy quantum supercomputers. And then what we did was we actually turned it into an ensemble algorithm where we're using them side by side, and we were able to improve on the state of the art in terms of detecting fraud. So artificial intelligence, machine learning, especially in the areas like classification problems and this kind of thing, fraud detection, pattern recognition, this is one of the areas that I think we'll see some very early results coming through in the next few years. And then finally, slightly further out than that, is that ability to model the future, is the ability to understand, from a wide and much more complex context than possibly we'd use today, many more dimensions, many more facets, the ability to do things like portfolio optimization or Monte Carlo type analysis of what the most likely outcomes are, and how to, how much money a bank would have to keep in reserve to maintain its regulatory stability and this kind of thing. So some very exciting longer term applications in the optimization space. So, and this I will not read out, but it gives you an idea of how many different places we think this thing applies, which is why we think it's so important. There is those base categories translate into an awful lot of real world applications. So for example, we've got Mercedes-Benz using the technology to develop new materials, new batteries, and the like. We've got people, ExxonMobil, looking at how you optimize the transfer of liquid natural gas around the world. That's relatively prescient at the moment, I think. When you've got a shortage of capability and supply, optimizing that, the traveling salesman, as we were talking about, problem is really important. JP Morgan Chase, looking specifically at futures using amplitude estimation and Monte Carlo type things to move forward on that. I apologize for my mad dog in the background. And also, they've recently published a further paper that follows on from their earlier work, which shows how using multiple quantum computers together with classical computations will mean that actually this becomes a reality much sooner than they were originally forecasting, because they won't require as many qubits to be entangled. And finally, as I was saying, CERN are looking at using quantum computation after the success of finding the Higgs boson to start investigating some of the other areas that they're finding intractable at the moment. So our view is that this is coming down the tracks. We can't tell you exactly when this is going to overtake conventional computing for these kind of tasks, but it looks to me, if I drew the graphs and stuck my own finger in the air, it's looking like 2024 is going to be the likely-ish kind of time frame. IBM is not going to tell you when it is, but if you were to extrapolate from what you're seeing at the moment, I think 2024 looks a pretty safe bet, actually. And the idea there is to really find a real-world use for quantum computing that we can show to the world and show that we are solving new problems that we couldn't do before. To get there, we're going to need more powerful computers. We've been building the number of qubits in our chips, and we've been increasing the coherence time, because all this relies on you being able to keep these quantum computational chips isolated from the vagaries of the real world and from the noise and from any interference, because anything interacting between the computational state of the quantum computer and the real world will collapse the quantum state. So we've been getting the chips bigger, but we've also been maintaining their coherence longer, which means we can do more work on the chips. And this is part of a much larger roadmap, which is is important to understand, I think, because it's more than just the fundamental engineering of the hardware now that we're working on. It's about making this consumable and making it accessible to people to actually understand and use. So you'll notice along the bottom here that the sizes of the chips get bigger. For IBM to be publishing something like this from IBM Research, I think you'll probably gather is relatively unusual. Normally speaking, if something's from IBM Research, or indeed any IBM chart talking about the futures, tends not to have years across the top, but this one does. So first of all, bigger, more powerful chips. Secondly, finding new ways to integrate them together. There are several different ways that we're looking at to actually ensure that multiple chips can act as one. So you don't need a 4,000 qubit chip. What you need is multiple smaller ones you can network together and maintain a single coherent computation across all of them. The actual way of doing that means that it's quite complicated to lay out an algorithm onto the chips, because you need to know what's the point at which you can cut the algorithm across the chips to make it the most efficient running on the chips. So we're working on the libraries to do that all automatically. So today you don't need to know that you're working on a multi-core processor. In the future, you won't need to know that you're working across multiple quantum processing units. All that will be hidden beneath the waves of the Qiskit runtime as we talk about it there. And even better than that, we've just sent live the first serverless capabilities, which allows you to actually interact with a quantum computer as if it was just a web service out there. You can ask it for a probability distribution from a series of algorithms or an estimate from a series of algorithms without really knowing anything about the quantum computer at all, simply by determining, here's my problem, here's the algorithm I want you to use, here's the output I want to receive, off you go. And that kind of process will continue, I think. We are seeing we've already, got quantum computers out in the wild. We've got them in our own data centers. We've installed them around the world. And increasingly, this is what it's going to look like. So this is a view from the top. Today, a quantum computer is just a single cryogenic chamber. That's the hexagon in the middle. In the future, what we're going to see is multiple hexagons wired together via fiber optics between the cryostats. And those control units coming out the sides, one of the latest things we just started to do is put the control circuits for the quantum computers actually inside the cryogenic chambers. This will massively reduce the power that quantum computers take, which is already an awful lot less than supercomputers take. And the racks down the side, you can see there are the conventional computers, or the GPUs, which are used to supplement the power of the quantum computer and control its execution of algorithms. And this is a beautiful artist impression of the machine that we're planning to release next year, which will do precisely that. So that was, I think, 30 seconds under 20 minutes. It was fast, but I'm more than happy to take any questions.
Well, don't worry, there's a surfeit of questions. And in fact, we'll start with a few. I'm going to knock off two quick ones and a long one from John Schlesinger. John's asking, Richard, is it still estimated to need 10,000 physical qubits to implement one noise-suppressed logical qubit?
Yes, it is, sort of. But we are pretty confident now that you don't need logical qubits to actually do something that's of real use in the real world. So in the latest announcements we've made, we've talked about how we're going to be doing error mitigation and doing that within the context of the actual quantum hardware itself, so that basically you can run an algorithm. But so yes, that is the right answer, but no, you don't need that to do quantum advantage.
Okay. John was also asked, how many of the 275 bits can be simultaneously entangled, and for how long?
Well, we're talking about, we're getting close to half to a millisecond. Yeah, so it's that kind of duration. All right. What we're really looking for is the ability to not just entangle them, but also then keep them entangled for 100 gate executions or whatever. Yeah. So the challenge we just announced is 100 by 100, which is 100 qubits for 100 gate executions, gate operations. And if we can do that, then we know we're in the in the ballpark of doing things that that no supercomputer could ever do. Yeah.
Okay. Just to show the audience is on the ball, and I'll come back to Richard Sage again with a real question, but he does point out that LNG carriers don't carry containers. Anyway, yeah.
That's a good point. Yeah, and my father was a marine engineer, and yeah, and believe me, bizarrely I'd seen that on the slide, and it hadn't actually sunk in. Yeah, yeah.
Okay. Maurice Schenk here, a little skeptical. Do you really have 433 entangled qubits that are usable for general purpose?
No, I mean, so let's be absolutely clear. All the quantum chips and their capabilities are published on the IBM website, so you can literally go in and look at the individual chips. So the 433 chip, the Osprey, has only just been announced, and just as when we announced the Eagle last year, it's not capable of doing that at this moment. Yeah, but that's the intention. You know, that's where it's going. So what you'll see is multiple. I think we're already on the second iteration of the Osprey, and you'll see multiple iterations of the same chip. So, you know, just as we did with the Eagle and the Falcon, I think the Falcon's on release 10 or 11 or 12 at the moment. You know, so what we're doing is using the smaller chips to improve the design of the bigger chips in certain areas, and using the bigger chips to solve other problems. So the bigger chips are really there to work out how we get the micro signals in and out of the machine without disturbing the machine, and getting the control circuitry working and everything else for the big. Whereas the smaller ones are what we're using to improve the actual individual gate performance and this kind of thing. So we're deliberately doing this in multiple different streams at once. Yeah, if we had 433 qubits that were stable for 433 gate operations, we wouldn't be talking about quantum advantage being in the future.
The conversation seems to be boiling around three areas. So artificial intelligence and intelligence questions, things to do with NP problems, and finally kind of usability. So just to outline where we might spend the next 10 minutes or so. Briefly, I guess what I'd probably like to start with is Trevor Hilder. Is it possible, or that the human brain does the same thing? And of course, you'll know the discussions of Roger Penrose and microtubules, but if you wanted to have just a quick canter through that.
My own personal view. I mean, I read Roger Penrose when I was in school. It's that long ago, but it convinced me then. It doesn't convince me now. All right. I mean, I think I'm much more of a thousand brains kind of man. That's a much more convincing explanation to me of how the brain works and why, and explains an awful lot of its weird capabilities and its faults. Much better, I think, than any Penrose quantum kind of explanation ever will.
Can you just give a 15-second reference on that one for the audience?
Yeah, so the thousand brains hypothesis is basically that the neocortex, which all looks very self-similar, is basically just a whole pile of tubes that go down and all do much the same kind of thing. And fundamentally, what you get is different parts of the brain specializing in different things that are all then connected laterally across from one another. But basically, essentially, when you have a thought, what it essentially is a consensus that's come to laterally across those many thousands of different tubes, which are part of the neocortex going down into the cortex. So it's a different way of thinking about the brain, because but it does explain an awful lot of why we're capable of doing of what we're very good at doing, which is synthesizing lots of different senses from different ways and synthesizing them into an opinion. And then sometimes that opinion will change and flip backwards and forwards in an optical illusion, for example, but we'll only ever be able to hold one opinion at the same time, which is another reason why possibly it's not really quantum.
I'll hold us to quantum now, if I may. But thank you. That was good to do that. So the second thing is, John Schlesinger's more substantive question was, quantum computers will not be able to solve the traveling salesman problem. It's an NP difficult problem. So he's holding up me as well as you. Why do you think the opposite? I believe quantum computers are not exponentially better, maybe just polynomially better.
Yeah, it has been shown that we can achieve a quadratic speed up. Okay, so that's been demonstrated. Yeah, but in reality, the algorithms that will be useful early on in quantum computers are those that can achieve an exponential speed up, which is not that many. Yeah. So traveling salesman is an exponential speed up, but it's just, it'll be quite some time before the inaccuracies and the overheads of executing that on the combination of conventional and quantum computing can be overcome to make it into something that's going to be, better than the state of the art in the supercomputing area. So yeah, I go with the halfway house on that one.
Okay. We've got quite a few here about encryption. Just let me read these off quickly. This is Peter Cousins. Whenever I read about quantum computers, the concern is raised that they will defeat encryption and passwords. Is that a real concern? Hugh Purser, from a security point of view, will legacy systems be at the mercy of quantum computing? Michael Kelly, will quantum computing present a risk to our current FS security models? For example, future central bank digital currencies? And finally, Jeremy Wilson, forgive my ignorance, but will quantum computing transform the practical value of blockchain? Which, Jeremy, I'm plumping here into the security issue as well. So some quick comments on that, Richard.
Yeah, I mean, put it this way. If things go the way we think they're going to go, then sooner or later, and it will be later, I mean, we're talking probably about a decade, 2 decades, 3 decades, there will be quantum computers big enough that's going to crack today's encryptions, yeah? Which means that if you've got data that's valuable now and is still going to be valuable in 30 years' time, don't let anybody nick it, even if it is encrypted, because they will decrypt it in, maybe it's 30 years' time. So we do need to be worried about this stuff. We do need to be thinking about it. We do need to be putting quantum safe algorithms in place as quickly as possible. We've already put them on the mainframe, yeah, for very obvious reasons, because a lot of the world's most precious data is held on mainframes. But the rest of the world is going to have to follow suit, and maybe it's not quickly, but it's the crown jewels first. The rest can follow at a slightly more leisurely pace.
Yeah. And a reminder to the audience that back in 2018, Maury Shank, who's online and asked a question, did a report which is in your chat room on the quantum countdown. Further, the Worship Company of IT is going to be holding some events with FS Club and Cien in March or April next year, very much not on do we need to move to quantum resistant encryption, but how do we set a date to move? And as a financial center, this is really important for us. Speaking of a financial center, Hugh Purser has got a question here for you, Richard. What does the economics of quantum computing look like? How much do supercomputers cost now? Will quantum computing be a rented or borrowed resource for the foreseeable future? Certainly that's been my view, that you've been moving to effectively hardware as a service online.
Yeah, I would have said that as well, and I'm sure that's our main intended model, is to go the serverless route and access the stuff via the cloud. Having said that, we've already put physical machines into the Fraunhofer Institute and into Cleveland Clinic and into, there are physical IBM quantum machines sitting out there in the wild. I think it'll be the exception, not the rule. Yeah, I think that there's obviously certain places for security reasons or whatever else, they may want their own dedicated quantum computer. But I think the vast majority of people will consume it, on a pay-as-you-go plan or as a, some kind of other, cloud-based plan. Yeah.
Okay. Then we move on to a set of questions, somewhat, I guess, looking at, well, what do you want me to do now? So, Maury Shank, the number of qubits required to solve problems like those you described is large. Certainly from today's current quantum computers, yet progress in qubit numbers has slowed in recent years. When do you expect quantum computers that can solve practical problems? Richard Sage again, if no quantum computer currently does something better than traditional computers, what are companies like Exxon actually doing at the moment?
Yeah, so there's some very good questions there. So my own personal view, it looks like 2024 to me. That's when that crossover point happens, where error mitigation, the size of the qubits, the coherence levels, and all these things, start coming together to overtake supercomputers. Yeah, at which point you've essentially a quantum supercomputer that's using a combination of hybrid technologies. in terms of the, sorry, what was the second bit of the question? There was a second element to it.
Second element, no, I think you've covered it actually. I think that's fine. We'll move on this one.
Okay.
Yeah, I believe that, one of the things that we're looking at here, of course, is complex modeling, really. And I've got two questions related to that. One from Bob Harris, which is some quantum computing models discover things, 3D structures of proteins. But if quantum computing is used to simulate very complex systems, for example, global finance, how does one? It's sort of on the edge of the subject area, but important.
Sorry, I lost you for that. You got to the as global finance, and then it just.
If quantum computing is used to simulate very complex systems such as global finance, how does one validate the model outputs?
You can't. I mean, it's another brilliant question, but all you can really do is the way quantum algorithms generally work is they're scalable by the qubit and they're scalable by the depth, and they tend to grow as a square. So basically, you put a more powerful problem in, the depth gets longer and the number of qubits gets more, and you can generally prove the algorithm's working. All you can do is infer that it's going to continue to work because you worked on the smaller problems until you got to the edge of where you could actually verify that it was still working. If you don't change the fundamental shape of the algorithm, you just grow its depth and you grow the number of qubits, but it's still fundamentally the same algorithm. You can infer that it's probably still working, but as you say, how do you prove it? You can't really, because there is no, you can control some inputs and check that the known outputs even in those extreme conditions are still true. I mean, there's various things you can do, but fundamentally, when you put in a really complex scenario, do you know that the right things come out? No, of course you don't. All you can do is observe what really happens.
Okay. I guess when we're examining this area, one of the problems is understanding the output here. And Richard Sage is asking just a bit of clarity.
Oh, I've lost you again.
Is output effectively always a probability distribution function?
No.
It is output from a QC.
Yeah. So the two types of output really. There's either an estimate, a number, which you can interpret how you like. For certain kind of problems, that's kind of like pretty straightforward. You still, to get that number, you probably had to run the circuits tens of thousands of times to get the number out. Or the other alternative is the probability distribution, which is going to be the output of multiple qubits run over even more circuit runs. So but pretty much everything either is one or the other of those. Yes. For some reason, I'm losing you. I'm not losing your sound.
Okay. Now, one of the things that I've always been curious about. Sorry, one of the things I've been curious about here has been whether or not Moore's law takes another leap. So you said 2024 would be the crossover point. What would you suggest people use to estimate the rate of speed up from that? Is it another Moore's law type approach?
Well, yes. I mean, the exponential. I don't know. I mean, we're using something called quantum volume, which is a very good measure of the usefulness of a quantum computer. Okay, which is basically essentially the number of qubits times the circuit depth that you can go to and this kind of thing, which we talked about before. So quantum volume is doubling, and it's doubling at least once, if not twice a year at the moment. So it varies, it hasn't quite stabilized yet, but it's definitely on a Moore's law type trajectory. And the other one is circuit operations a second, which is much more familiar to people who followed IBM a while. If you're used to MIPS and everything else, then CLOPS is the new MIPS. And CLOPS it's the so early doors of CLOPS at the moment that it's going up by many orders of magnitude so far every year. So I think it'll take a while to stabilize because I think the gains are so large at the moment. It will stabilize to a Moore's law type thing, but what it will stabilize at, I don't honestly know at the moment.
Okay, and a final question from the audience. This is from David Penny. How do you think we can begin to use quantum computing capabilities to address machine learning? Um, any
Yeah.
thoughts on?
So that was, so that I remember the second half of the question now, which is why are ExxonMobil using it if they can't get quantum advantage? The thing is, you can build the algorithms now, okay, and you can test them and you can see their work. I mean, I was talking about the smarter payment stuff. We're able to now use the quantum computers even as they stand to get small state-of-the-art improvements in accuracy on real-world problems. Okay, now we can't use that in the real world yet because Visa and other people have got slightly higher transaction rates than my quantum computer can cope with at the moment. Yeah, but but fundamentally, you can start building the skills and building the algorithms, and as the computation capability gets better, and as the circuit depths get longer, and as the number of qubits get, those algorithms will play out in that ability to take on board more dimensions of the problem or simply get more accurate. So that's why we've got all these people. We've got over 150 companies and organizations, I think, now in our quantum network, who are all working simultaneously on these kind of problems, because they know that if they crack the problems now, that when the hardware becomes available and the software becomes available, for that matter, in the forms I've been talking about, that they'll be in a position to use it.
Okay. So the final bit was we're going to ask a little question on to the audience. Do you think quantum computers will change the world? So I'll just launch that question now. We've heard Peter. Peter, whilst the audience is answering that, and again, they're as quick as ever, I was curious about, I've always said that it's not about smaller, cheaper, faster, it's about different types of problems. And I've used two analogies to try and get it across to business people. One is that this is a bit like those crystal ball or at-risk Monte Carlo simulations, but done instantaneously. And another one, somebody who started on analog computers in the early mid-70s, that it's very much an analog computer type approach. You set the physical system up and it delivers the answer. Any comments on those two analogies?
Yeah, I think. I mean, the first one is not a perfect analogy. The second one, I think, is closer, actually. And by the way, watch this space for analog computers. I think they're going to make a comeback.
Yeah.
I think one of the ways we can really reduce the machine learning costs of large-scale machine learning algorithms is by using analog computers. So don't expect that technology to disappear. I think it's going to come back in earnest in the near future.
Yeah. Well, what you also saw there was that you're an excellent ambassador. You've convinced the audience, almost three-quarters, that quantum computers are going to change the world. Sadly, we have run out of time. I think it's been absolutely fascinating to see, really what a great ambassador you are, Richard. And we've covered a lot of things, exponential versus polynomial or even logarithmic time and speed up, PNP problems, theories of the brain, economics, encryption. I mean, the great thing is the sign, I think, of a revolution is when it really does genuinely touch on so many areas of interest to all of us. So thank you very much for coming on board today. And I can tell that we're going to have you back many, many times if you'll let us. I think each year as we try and see what is the progress of this fascinating technology that three-quarters of the audience thinks will change the world. And I'm afraid I'm with them on that. So thank you very much.
Michael and everybody who joined, thank you for your time. Much appreciated.